Okay, good morning. So I guess students are running late.
I'm doing the homework.
Okay.
The problem one, part A, is similar as the homework one. The homework one, problem 3, A and B.
A little, yeah.
Similar with that.
Okay. Give it one more minute for folks to log in. So how is everybody with Python now? Are you starting to be able to use it? Is it okay?
It's all right to use so far.
Okay. Because I was thinking I may want to start assigning questions for homework with Python. But I want to make sure that, you guys are kind of starting to be comfortable with the language, with the concept before, I start assigning homework questions on that topic. Does that seem okay, or you need a bit more time to get used to, concept, the language? Anybody? It's okay if you're not comfortable.
It's fine.
Okay.
I mean, it would be a nice way to help us learn about using Python.
I think so. Yeah. I mean, I could just do it as, review session as the last 2 weeks, but I feel, if you don't get your hands on trying to think about this a little bit, right?
Mhm.
You may not get as much practice as you're required to, or as you should. So putting it as homework questions might kind of point you in the right direction. Okay.
Okay.
Right. All right. So again, right, is as I said, I think all of these are quite useful, all right, in the long run. So even though I know it's not like exactly part of the class requirement, but I think it's good to incorporate that in. Okay, very good. So let's begin then. So last time we were in the middle of discussing the so-called idea of Ito calculus with so it kind of separates into two topics: the Ito integral and the Ito formula, or I think Professor Larson would refer to as a Ito's lemma, or whatever. So Ito integral. So So what here it deals with the derivative, as I'll explain. So first of all, right, the whole idea of integral is how to define or how to make sense of the integral fs dws. And the derivative is kind of the opposite, where, let me tell you, right? So the idea is, given, right, a function of two variables, t and x. T stands for time, x stands for the Brownian motion. How to represent this function plugging in time and Brownian motion as, so basically the idea is, let's say it starts from a time s, okay? And then from s to t, there is some change. The change comes from two parts, right? The first part is a change in time. The second part change from the comes from a change in Brownian motion, right? So you understand that, sorry, du. Okay. The point is, right, as s move to t, so let me put a question mark here. As s move to t, right, from this interval, two things change, right? Of course, time changed, but also the Brownian motion values themselves change, because Brownian motion changed implicitly through time. So, right, so we want to capture this change, right, the change in the function via the change in these two components, right? And that is the two question mark. So that's the essence of Ito's formula, which we'll discuss today. So I want to mention this because I want you to see that this is nothing new. It may be presented in a little bit of a new language, but this is the same as before where you looked at the fundamental theorem of calculus. Okay. The fundamental theorem of calculus would say this, that if you just have a function in t, then it's going to be the function value at time s, and the change from s to t is the derivative of the function. Okay, like this. So I hope this is not strange to anybody. This is something you have seen before, even though maybe you don't use it as much. For example, right? What is it? Suppose that the function itself, let's say, is e to a t, right? The easiest one. Then you got e to a t, right, is e to a s plus the integral from s to t, e prime, oh, sorry, not e prime, right, e to u du. Right, this is true, and you can do it just by your antiderivative formula. You can try anything else, like let's say t squared, then we got t squared is s squared plus 2u du, right? These are very familiar with you. But again, right, try to not see it as formulaic, meaning, well, I got a formula, I plug in, I got that. Yes, true, right? But the formula is meant to tell you something, okay? What it tells you is, again, that the net change, right, of the function value as time moves from s to t is captured, right, by the derivative of the function with respect to time. So that, from that angle, you see, when we have another component that is captured by the Brownian motion, then this is just an extension, or is really in the same spirit as the fundamental theorem of calculus, where, okay, as time moves, now not only time we have a change in the time component, but we also have a change in the Brownian motion component. Okay, and how do we capture that? So the question mark here, if I were to put it, is captured by the derivative of the function with respect to time in the if the function were to be independent, okay, of the Brownian motion. So we'll be talking about this today. Okay. Any questions so far? All right. So now, what I want to do next is to go back to the idea of the Ito integral and kind of reinforce it some more. So for Ito's integral, right? The difficulty of the Ito's integral, okay, or the subtlety of the Ito's integral is as follows. So if you have a process, okay, f of s that is adapted to the Brownian motion filtration, then if you were to and you have time from 0 to t, okay, and you do a division, a partition, okay, so this is a partition of the interval from 0 to t, right? And of course the length, right? The partition size. Let's just call it, right? Something like delta t, right? So, and suppose it's equal size. When we do this, right? When we do this object, let's say fti star, okay, wti plus 1 minus wti, sum from 1 to n, right? This is called a Riemann sum. Or yeah, let's just call it a partial sum. Let's not call it a Riemann sum. Okay, it's a partial sum. And this is so in a way, right? This is very similar to, you know, the kind of the what you call it, the Friday activity you did last week, where so the activity last week where you do, you know, like the integral, right, of f of let's say the integral from, I forgot already, but like let's say the integral from a to b of f of s, right, dgs, and you ask to calculate what that is. Okay, and so the suggestion there, right, was you try to approximate this with the partial sum. Okay, and you try to, right, push the delta t to go to 0. So here's a question, right? Do you remember what the message of the problems from the last week's activity was? What is the issue with the choice of G here, or what were the results when you asked to do this, when you asked to explore this problem? Anyone remember? So there are two cases, okay? the first one is when G, right, is differentiable. If G is differentiable, okay, if G is differentiable, then the integral of course in S will be this G prime of S ds. Okay. But so and you were asked to explore this question and to check that this is true. The other case, right? But if G is not differentiable, it's not asked to, you were not asked to explore because it's kind of hard to come up with an example for it. But exactly, you know, the case where G not being differentiable is the case we have in hand with the Brown motion. Okay, because you see what happens is this function G right here, right? What we write in the abstract is the Brown motion in this case that we're looking at in the ethos integral. And the point is that the integral, okay, so the integral f of s dgs is not well defined. So when you try to, right, this is called the integrator. When the integrator is not differentiable as a function of time, then this integral that we try to define, right, against this integrator may not be well defined as the limit as the partition size go to 0 of the partial sum. Okay, so I want to kind of illustrate this phenomenon for you. So first of all, right, that here when G is not differentiable, what I'm trying to capture is exactly the Brown motion. W, right, is nowhere differentiable in T. Okay, so that's exactly what I'm talking about. But the illustration from last time, so from the last week's activity, what you did was you tried to do, so you asked to look at the integral from a to b square root of ds. Okay, and you asked to see that this goes to infinity as delta t goes to 0. Okay, in your activity. And what's the message there? The message there was this, that when you take the square root of the differential, okay, you take the square root of the differential, this term gets large as dt, I mean, it's larger, right? Okay, so square root of dt is much bigger than dt as dt goes to 0. That's the message. All right, so that's why this integral or this partial sum is not convergent as dt goes to 0. And again, what's the relation to the Brown motion here? This integral you asked to investigate is very much connected to the Brown motion because remember, right, the differential of the Brown motion, roughly speaking, is the normal random variable with mean 0 and variance dt. So in other words, right, what we're saying is the variance, right, of the dwt or expectation of the square, right, of dwt is dt. Okay, so fudging some details, this is saying dwt square is dt, and actually this will be made precise later on. Okay, but you see, because dwt square is dt, roughly speaking, you're saying dw is square root of dt. So that's what I asked you to explore right there. Okay. When you do this, you were kind of replicating the integral like this. But it's clear that in that case, this integral goes to infinity. Okay. Now, so, but what's the difference? There is some slight difference here. The difference when you go back to the dwt term like this is the fact that the dw, right, the change in the Brownian motion, have sign. So even though this is like square root of, right, ti plus 1 minus ti, when the delta t gets small, it can have plus or minus sign. Okay. It can be positive or it can be negative because Brownian motion, right, doesn't have to always go up. And the consequence of that is, even though, you know, this sum right here diverges to infinity, there's still a hope that this sum converges. Why? Because it's like the sum of alternating series. Okay, this is like a sum of alternating series. So, for example, the sum of 1 over n, okay, or like this, 1 over root n, that's kind of like this. As n from 1 to infinity, this is infinity. But the sum of minus 1 to the n converges conditionally. Okay, so we say this kind of convergence is conditional because its absolute value does not converge. Does anyone remember this kind of knowledge from your calculus day?
Yeah, I do.
Okay. Do you remember what's the big deal about something like this converges conditionally? So we say, right, this conversion is conditional, right? Not absolute. What's the difference? So for example, right, something like this is absolute convergence. Sum of 1 over n squared, n from 1 to infinity is finite. Sum n from 1 to infinity minus 1 to the n, 1 over n squared also converges because of this, right? You don't need the alternate series to say it's convergent, and it converges, but it converges absolutely. What's the difference? So the difference is this, all right, that when you have a conditionally convergent series, if you rearrange the terms, the target will still converge, but it will converge to a different sum. So what happens is this, right? For example, if you have 1 and then minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, etc., right? So this is the sum of minus 1 raised to n over 1 over n like this. This converges, okay? Conditional converges by alternating series tests. But if I rearrange the terms, okay, if I rearrange the terms, so if I do something like, let's say 1 plus 1/3 plus 1/5 plus 1/7, and then let's say I do minus 1/2, and then plus 1/9 plus 1/11 plus 1/13 minus 1/4. You see what I'm doing, right? So instead of doing a plus minus, I add 3 terms, for example, and then I subtract 1. Add 3 terms and subtract 1. This still converges, but it will still convert. But the sum, right? This sum and this sum will be 2 different numbers. Okay. I'm not sure if you have seen this kind of knowledge before, but it's really a interesting piece of information, and it has real implication. Okay, it has real implication. The implication for us is exactly here, where what I was asking you to explore in last week's activity is something that says the Brownian motion does not converge absolutely when you use it as an integrator. When you use it as an integrator, it does not converge absolutely. So it converges conditionally, okay? Because the Brownian motion can have plus minus sign. So it kind of helps it to converge. It doesn't always go to infinity. But on the other hand, what happens is the limit here depends on the choice of where you put the Ti star. So Ti star, if you remember, is any point in between the interval. So this is T1 star, T2 star, okay? What happens is this limit as delta T goes to 0 of f of Ti star, okay? Ti plus 1 minus Ti, like this, is supposed to converge, let's say, to the integral from 0 to t of f of s ds, no matter what the choice of Ti star is. All right. In other words, suppose you choose from 0 to t. Here's T1, here's T2, right? Here's T3. You could choose the left point. So this is T1 star, T2 star, T3 star. You can choose a left point. You can choose a right point, T1 star, T2 star, T3 star, or you can choose the middle point. Okay. Any choice here, right? When you do the partial sum, will always converge to a same and single number, this integral. On the other hand, right, when you take the limit of the Brownian motion differential, okay, this limit depends on the choice of Ti star. So this sum will converge to a number, all right? This sum will converge to a number, but this number, whatever it converges to, depends on your choice of Ti star. Is that okay? So in other words, if you choose a left point, you get to one number. You choose a right point, you get to another number. You get a midpoint, you choose a midpoint, you get to yet another number. So the Ito integral is the limit of this partial sum when the Ti star is the left point. That's our choice. That's what we mean when we say Ito integral. There is another one that's called the Stratonovich integral. When Ti star is the midpoint. And the point is that these two guys, these two integrals, are different in values. Okay, and so when we say that, you know, there is a difficulty when you define the Ito integral, or you have to be careful, right? The Brownian motion does not, you know, is non-differentiable, that kind of thing. It ultimately boils down to the fact that this partial sum converges to different values depending on the choice of the Ti star. And you must be careful, right, which here I start you choosing when you mention the integral of your choice. So Ito integral always use the left point as the limit. Another integral can use the midpoint, for example. Okay. Question on this? All right. So that seems a little bit abstract, right? But let me show you. A demonstration of this, and you see. Okay, so here, right, I generate a, oh, hold on, I did not. Okay, so here I generate a Brownian motion, you see, by adding a dw. And I'm considering two different types of integral. And actually here, right, the integral I'm looking at is the integral of w dw. The integral of from 0 to, let me see, the integral from 0 to 3, right? Because t is 3. I do the dt like this, and I look at the integral from 0 to 3 of w dw, okay? And as you see, right, I form the partial sum, right? I form the partial sum by letting, right, w times dw, right? Because it's the integral of w dw. But notice, right, here with the Ito integral, because dw, right, is wi plus 1 minus wi. So that's why I use the left point here. You see, wi plus 1, right? Plus, so dw is by definition of my construction, right? Here you have to be very careful with the array in programming, because you might choose the right point, you know, by mistake. But here, dwi is wi plus 1 minus wi. Now, with the Stoyanovich integral, you see, I choose the midpoint. Okay, I choose the midpoint, which is the half, right, of the wi plus 1 minus wi. All right, this is a midpoint. So if I choose the midpoint, and I sum it up, right, you'll see that these two converge to different numbers, and I'll show you. Oops. So this is a Riemann sum, okay, and this is the Ito integral. The Stoyanovich integral converges to this number. All right. So in other words, when I form this sum, I got 0.29. While on the other hand, on this sum, I got minus 1.24. Okay. So you see how these two sums are very different in their final output. How these two sums are very different from their final output. And so that's what I'm trying to say when I say, right, that the choice of the point, right, will change the value of the integral. Now you see that if you were to just do the regular integral, okay, if you were to do the regular integral of like the t dt, then these two will converge to the same number. These two will converge to the same number. But here they converge to two different numbers, depending on the choice of w of the point. And that's the message. Okay. So with the Ito integral we have in mind, we always talk about the left point, left-hand point, and not the midpoint or not the right point. Any question on this? I think it's a little bit subtle, all right, but it's really the essence of the Ito integral like this, and it explains all the weird formula, maybe weird, that we'll be doing with the differentiation. So understanding this point will help you appreciate why we bother going into, all the definition later on. Any question on this? Okay. So let me just write down one more thing, okay? So the definition of the integral, so the definition of the Ito integral is going to be the limit as the partition go to 0 of the expectation, okay, of the partial sum minus whatever this target is. So this is the definition. So in other words, right, 2 points here, that here is always the left point. And second, there is this mysterious object that I don't know, but whatever it is, when you form the partial sum with the left point and you look at the target, on average, the difference, right, the difference square goes to 0 as the partition size goes to 0. That's what we're saying, okay? Mathematically, rigorously, you can say that this allows you to define the limit as the limit of a Cauchy sequence, but we won't go into that, all right? I'm just gonna put this here. And the point I want to emphasize is the left point, okay? The left point choice of the partition. So, okay. So this carries with it a bunch of consequences, right? So again, so properties of Ito integral. So again, right? So if you have a process that is adapted to the Brownian motion, then the following holds. First of all, this is also a process, a stochastic process. That is adapted to the Brownian motion. Filtration. Its mean is always 0. Its variance is always this. Moreover, if Fs is deterministic, independent of W. So in other words, if it only depends on time, okay, only depends on time, then this integral is a normal random variable with mean 0 and variance like this. Okay. So, for example, when I want to assign you Python homework question, it's something like this. Write code, write simulation code to verify ABC. Okay. So because the point that I want to make in this class is right? All these are, well, I understand they are abstract knowledge. But one thing, right, as a, I don't know, as a practitioner or as like an applied person, okay, which I hope you all are, is you can have a way to verify or to bring this to life, to see how they are, to verify them at least computationally with your computer, with whatever it is. Okay, that
Um,
that's the
so basically, they're
yeah,
just like basics that demonstrate these properties.
correct, with the code, right? I mean,
Okay.
I hope that you see that the code I've been writing so far or showing you is to demonstrate all these properties of the Brownian motion that I try to convince you on paper, right?
Mm-hmm.
It shows you this. So now the table is turned on you, right? You tell me how you would verify this. Because unless you question, all right, unless you question the idea and the meaning of this, and you write code to see it, you won't be able to, you know. So for example, how would you write a code to demonstrate point A? Right? So for example, so what you want is some pseudocode. In other words, just describe things in English. What would you do to demonstrate?
I'm not sure.
All right. So first of all, right, the the math is stated in very abstract language, right? It says for any process like this works. When you write code, clearly you cannot. So you cannot, demonstrate true for any, right, function. So you need to choose one.
You need to choose code that's function that's within like.
So first you want to choose the integrand, right? What choice do you, what choice would you choose?
Just S.
S is an okay choice, right? But S is a little special. Why? It's an okay choice, but S is a little special because it's deterministic. So
Oh, I
maybe
see.
you can reserve that for the choice C, right? But when you do A,
Okay.
maybe let's choose WS,
Okay.
right? So what are we doing? You want to simulate this, right? So how would you simulate? Let's say this. How will you simulate this? Well, you need to, right, simulate WT, right, WS on 0 to 1. So before that, right, you must do partition of 0 to 1 into subintervals. Then you simulate this, and then you do the partial sum. Okay. Is that okay? That's one simulation of this. Now, how do you, the question asks you to verify the expectation is equal to 0. How would you do that?
I'm just thinking of it in a like naive way, But could we just run like a bunch of them and then just average it out?
Absolutely, Sherry. That's all I ask.
Okay.
That's all I ask. Repeat step 2. Take the average. And if the theory is right, what should the average be?
0?
Correct.
Wait, I think, yeah.
Okay. Now, actually, right, I say this is like homework, but I think I even wrote the code for you already. So let's see. You see right here in the second part, right? This is the number of simulations. This is what I said, right? This is the repeating step, right? This is repeat step 2. This is the generate the Brownian motion right here, right? This is generate the Brownian motion. So of course, right, you need to simulate the DW. That's the Python part, right? That's the technical part of Python. It's taken care of for you right here. Then you generate the Brownian motion, right? Then you generate the DW. This is a partial sum, right? So right here, right? This is generate the Brownian motion. This is generate the partial sum. Is that okay? And then, right, and what do I do here, right? So this is one partial sum. Okay, do see the code. This is within, right, one path. I generate a partial sum. Then the first moment, right, is this is what Sherry was saying, where I keep repeating and I keep adding it. I keep adding this result. And what do? I divide it by n, and I output the result. Is that okay? And let's see, right? Right here, you see? 0.005. 0.05. And right after you do this, in all reasonableness, you can conclude that the expectation of WT dWt is 0. Is that clear? How this demonstrate the expectation of W dW is 0?
Yeah, I think it's clear.
Okay. Yeah. Thank you, Sherry.
I have a question about one of the properties, just a minor question.
Yeah, sure.
For the variance one, is it, because I think I wrote it like the flip last time, but I'm not sure. Is it the integral from 0 to t and then the expectation of f the process squared, or is it the expectation squared?
You tell me, which one?
Oh,
What is the expectation square?
is it just expectation squared?
No, your question makes sense, right? And sometimes this gets confused. But if I were to tell you this, which is the expectation square? Yes. Or if I were to be more careful, I do this. Right, that's what we mean by expectation square, right?
Yeah. Okay.
What should this be?
Should this be 0?
Yeah, because right, I mean, just change what you said, right? Is that you square this, but we set this as 0. We demonstrated 0, so it must be 0. So whatever I was saying, right, was something like this. Let's say, right, is equal to this, right? What must I mean? I must mean, because this right here clearly is non-zero, right? So I must mean the square inside expectation.
Okay. Yeah, I think I made a mistake with my notes last week then.
Oh no, that's fine. That's fine. Again, it's very easy to mistook this. But what I'm trying to say, right, is if you put your knowledge together, and you should notice some inconsistency right away, because
yeah.
if we were to do this, it cannot be something non-zero, because that will flatly, right, contradict property A.
Okay, yeah, thank you.
And coincidentally, right, that's why I could write a variance of this is equal to that. Why? Because the variance is
The
expectation of the square minus the square expectation.
yeah.
And because expectation is 0, the variance is nothing but. So what I wrote here is not, right, different from. Is that okay?
Yeah, that makes sense. Thank you.
So having said that, right, how would you write a code to simulate the second part, or to verify the second part B? How would you write the code to verify part B? This property right here. So step A is the same, right? Obviously, you must choose something. So let's stick with this. Step 2, what do you simulate? So you still partition this, you still simulate this, right? But you need to simulate the square, right, of this. Okay, you need to simulate the square of this. So this is B. Okay, and how do you simulate the square of this? By squaring the partial sum, right? And then you repeat and you take the average. But what should be? What should the average be in this case? What should the average be in this case? Or what, Don?
I was gonna say that the average should be like the integral of fs squared, but that's our result. So.
No, yeah, but what is f of s here?
Oh, right. It should be t squared over 2, I believe.
Very good. So the
Wait,
average.
Yeah.
The average should be the integral from 0 to 1 of SDS.
Yeah.
Should be,
It should be
1/2. Agree?
Yeah, that's right.
Yeah. So let's
see the endpoints. So
yeah. So let's see, right? Let's see that we have that. So I must change, right? So here my t is 3, all right? So I change it t to 1. Doesn't matter. I can stick with t equals 3, actually, I think. Right. And so you see here, right? Oh, am I sharing with you? I'm not sharing with you, right? Am I?
you're sharing.
Okay. So here's the second moment, right? And the second moment you see is I just add the square of the partial sum, like I said, right? And I divide by n. Okay. Now, obviously, right? Obviously, so what should this be if t equals to 3, right? If t equals to 3, then what should this be? 4.5, right? Because it's going to be 3 squared over 2. Now, I mean, let me just change it to 1 so that, go back to what we say. So, but I was lazy to calculate this, so I just, I was just running a, calculation, right? A numerical integration. But you see the numerical integration comes out to be 0.5, right? and you see the simulation comes out to be 0.479, right? Now keep in mind, right, the more simulation we make, the closer this is. So this will never change, right? Because this is the theoretical one. Takes a while. Yeah, see, it's much more precise, right? It's 0.50. Is that okay?
Right, I see that. Okay.
So these kind of questions, right, is what I would want to leave for you to explore a little bit, okay? Because like I said, right, I mean, this class can be taught completely in the abstract point of view, meaning, you know, I tell you the thing, you do the formula, etc., like the homework, right? And of course, there's a place for that on the homework and on the midterms and exams, things like that. But on the other hand, right, I want you to see that these properties are very, very realistic or physical in the sense that if you want to, yeah, you can code it up and calculate it. It's right there in front of your eyes. It's just a more sophisticated calculation when you can do the calculation, all right? I mean, this is not abstract formulations. What about C, right? C, I did not write any code. How would you code something to verify C? So C can be really your homework, right? How would you code something like C?
We plot a bunch of the, integrals and then plot a bunch of the normals using those that mean and that variance, and then just plot them on the same graph to compare.
I think you have the very good idea. So first of all, right, you got to be a little bit careful when we do C. Are we using the same setup as A and B?
No, it has to be independent of the
Yeah, so we need to have a different choice, right? So
yeah.
the choice will be something like S, right? So for C, you must be careful not to choose something involving W. So maybe WS, so S, right? Like Don's suggestion is fine. But second though, right, Sherry, when you say you plot a bunch of this and plot a bunch of normal, what do you have in mind when you say that? What exactly do you mean when you plot the normal? So I understand what you mean by plotting this, right? Because that's just plotting it.
I
But
guess like just to have the term on the right to I don't know how to do it yet because I'm not that familiar with Python yet, but I was thinking
no,
like
it's really, it's not even Python, it's a conceptual question.
oh,
What
okay.
we mean when we, well, so roughly speaking, maybe I understand what you mean by plotting this because it's a bunch of numbers.
Yeah.
But still, right, be careful there. You plot a bunch of numbers against what? Because plotting always kind of sort of mean Y versus X. Yes.
Yeah.
So
Oh, okay.
by the Y here, you mean these values, which X are we talking about? All right. That's where like somehow when you do coding, you see that a lot of practical questions you don't consider comes in mind. So yes, some kind of plotting, I agree with you that will bring it home. What kind of plot? But so the left-hand side from your suggestion is not that clear yet.
Yeah.
But the right-hand side is completely unclear because what do we mean when we say we plot a normal?
Would we just be looking at the final result, like the number, not the X in this case?
Number though.
Like
What?
I'm just thinking, would we only be looking at like the Y, for example, and then just having a bunch of Y values? Or
Sure.
am I off the bat?
No, that's very good. You have a very good thing in mind, but do you know what object you're looking at? You're thinking about?
Um, is it? Oh,
There's a word for it.
oh, I don't know.
It's fine. It's called histogram. you're thinking of exactly a histogram. All right. So yes, but you see, without nailing the right concept, then you won't be able to, call the right function from Python or even look it up, right?
Yes.
So what happens in part C, as Sherry was saying, right, is so first choose this, okay. Second, you simulate, right, this, but of course it becomes SDS, WS now. Third, right, you compute the partial sum, but now it becomes TI, right? And so then you repeat step 2, but you don't take the average, okay? You don't take the average because part C does not say anything about the average, right? It's not about expectation, but it's about comparing it with the normal. So what you do is you plot the histogram, right? As Sherry was saying, you store a bunch of these values, okay? They are Y values. The histogram, right, will kind of tells you, right? So here, the histogram actually is Y and Y count or Y frequency. That's what the histogram does. And so, right, when you plot the histogram, you should see a bell-shaped curve. And that's the proof that, or that's at least the visual verification that this guy is a normal distribution. And if you want to go above and beyond, which you should, because not only this, right, is also verifying this, you can plot a normal density on top of your histogram. A normal density, right? And sorry, by the way, actually it should not be this, right? It should be, because it has mean 0, so it should be in the middle like this. That's your histogram. Your histogram should look like this. And you can also plot a normal density on top of this, the normal density with this kind of variance. And of course, right, what variance are we using? Because of the part 2, if we choose S, it'll be 1/2. Oh no, it's S squared over 2, so it's 1/3. But the normal density will be very close to your histogram, okay, if you want to do that. Any question on this? So I'll leave it for you, right, to explore as a homework question.
For part 3, how many times do we repeat part 2?
Say what, Don?
For part 3, how many times do we repeat part 2?
That's also a question for the coder, right? Meaning,
I see.
Right? Because here, right, that's exactly the kind of questions that arise in coding. It's not about pseudocode, because you see before, right, I did 1,000 simulations. I look at the average. Is it close enough to 0? I don't know. I mean, depends on your taste, right? But right. So the more simulation you make, the more the histogram looks like normal, maybe, right? But of course, right here, the suggestion should be you should do more rather than less simulation, because right, the convergence happens when you have more simulation. But on the other hand, right, the point is that from a practical point of view, if you do too many simulations and no one has half an hour to sit around and wait for your result to load, right? Okay. So you have to do balancing, which is exactly the whole point of coding, right? Efficiency, just, I don't know, results.
Okay.
Any question? Okay, so start thinking about these things, right? And soon enough, you'll see that this kind of technique can be used to demonstrate many things that you learn from many math courses, right? Because at the end of the day, behind, right, any math result is some kind of calculation you can do. I mean, well, at least applied math, right? And so if you cannot do the calculation to back it up, that's a little troublesome. But of course, I do understand there's a part of math for that. But like bringing the calculation to life, right? Plotting the picture, printing out the numbers, right? Are, I think, part and parcel of what you will be practicing in real life, right? Because what's the point of pricing if not output a number, right, that your client can use, right? If you cannot output a number and just say it's some kind of bright motion, well, no one's going to hire you, right? Any question? Okay, so let's go to differentiation, okay, which is Ito's formula. Okay, so with Ito's formula, right, the goal, like I said, is to be able to express, right, given a function, okay, and I'll use this notation, C12. It's really just, we won't really mess around with this assumption, but it just means once differentiable in T twice, right, the 1 and 2, differentiable in X. I think you might have seen this in numerical analysis or something. Okay. I mean, most of the things we do will be like this. And we want to express, let's say, the value, right, the value of this function as some terminal time, as this value of this function at some initial time, plus some integral ds and some integral dws. Okay. Now, so you understand, right? So this is like the representation of a function of Brownian motion in terms of this is Riemann integral and Ito integral. Okay. Of a function, right? F of t wt as a, let me call it a dt integral and dwt integral. And apologize, I wrote the limit wrong, right? This is the limit from s to t, and I should change it to u. dwu. Okay. Now, without further ado, I would tell you the answer. The answer here is a partial with respect to t, and then 1/2 the partial with respect to x twice. Okay. Everything here is the dt integral. And here is the partial with respect to x. Okay. So first time anyone see Ito's formula, they will be overwhelmed because there are too many things going on. But actually it's very simple. Just keep in mind there are two variables. One is time, one is space, if you will, right? Space is controlled by the Brownian motion, time is time. So when you integrate with respect to time, there are two aspects. First is a change with respect to time. But the second, more surprising aspect is the second derivative change with respect to Brownian motion. We'll talk about that. When you integrate with respect to Brownian motion, it's just straightforward. It's the change with respect to Brownian motion that we're looking at. Okay. So any question about this? We'll do a bunch of examples, okay, to demonstrate this idea. So don't be afraid. But maybe abstractly, any question on this? All right, so let me give you an example, right? Or a bunch of examples. Let's say choose the easiest thing. Okay. So when you're not used to it, all right, maybe you should try to go back to, by the way, right, one of the question I usually get is, this X confuse people. This X confuse people because they're like, there's no X in here. This X is a notation that refers to the original, right, writing of F. Oh, by the way, right, let me emphasize this so I don't confuse you. This F is completely deterministic. In other words, it has no Brownian motion in it. So it's rather a unfortunate choice that, you know, up here, I know I used this something, right? This right here meant a stochastic process. So you see, it may or may not be a function of W, all right? Here, when I write this, they are kind of somehow related in a way, but you know, the relation is not really, this F is that F. But this right here is just a completely deterministic function. So when I say f of x and f of xx, what I mean is take this formula, all right, and differentiate it, and then plug in w in place of x, okay, as you see. So again, that's the confusion that I usually get. Now, of course, if you want, the alternative is you can do this, f of w, if you want. W stands for the differentiation with respect to Brownian motion. And if you understand what you're saying, then I think I have no issue with that. But you know, traditionally, people would use x, okay, in place of w. So let's see. So if I write like this, then what is f of tx? What is f of tx?
Is it just x?
X squared.
Correct, right? I asked this because, you know, what is f of t?
Zero.
Yeah, f of x.
2x.
Yeah, f of xx, it's 2. I hope. So it's as easy as that. So this formula would say wt squared, right, is ws squared plus the integral from s to t of, you know, 1/2, right, times 2, the let's say the u, right, and then plus the integral from s to t of 2 wu dwu. Is that okay? Now, if we can eliminate one of the point, right? We can make this more even concrete. We can say let s be 0. So if that's the case, then what's w0? Oh, sorry. Why do I write minus? It's plus, right? Plus. If s is 0, then w0 is 0, right? So, and usually people put the Brownian motion first, okay? So it will be 2 integral from 0 t of wu dwu plus, right, the integral from 0 to t of du, or, you know, this is just t. Any question? Okay. Another example. Let's say f of t wt is e to the mu t plus sigma wt, where mu sigma are constants, right? You know what we're talking about here, right? This is the prototype for your Black-Scholes formula, for your Black-Scholes model, right? I just take away some of the, you know, more complicated bell and whistle, but at the heart of it, right, is exponential, something t and something wt. Okay. So what is the function in terms of t and x? e to mu t plus sigma times x, right? What is the function differentiate in terms of t? Well, there are many things to do, but I hope it's just mu times t. Sorry, mu times f, right? And f sub x is sigma times f. F sub xx is sigma squared times f. Is this okay?
Yeah, that's okay.
So thank you, Sherry. So plug in, right? You got f of t wt, right? Or rather, right? So yeah, so e to mu t plus sigma wt is, you know, let's say, right? Let's pick s to be 0, right? Let's pick s to be 0. Then you get, when you have 0, right? When t equal to 0, this is 0 and this is 0, so that's 1, right? 1, and then plus the integral from 0 to t of differential respect to x. So sigma, right? And let me just do this. E to mu s plus sigma ws ds. And plus the integral from 0 to t of, sorry, not only sigma, right? I'm talking nonsense. Sigma dws. And then in terms of the ds, right, it's going to be sigma, mu, right, and then plus sigma square, plus 1/2 sigma square, e to the mu s plus sigma ws dws. Is this okay? This is the f sub x dw, and this is f sub t 1/2 f sub xx. Oh, sorry, ds. Okay, it's very easy to mistake these things. So again, right, pay attention. The differential with respect to Brownian motion dw, the differential with respect to t, and the second derivative with respect to du. All right, so I hope if there's a question, let me know, okay? So a quicker formulation, or I mean, a differential formulation, will be something like this. So instead of writing the integral, okay? Instead of writing the integral like this, I'll take a clue like this, okay? We understand the following. The integral from from s to t of any differential will be the big difference between, right, the function at time t and the function at time s. Okay. The differential of any integral something like this will be f sub t dt. The differential of any integral, sorry, f of u dw, f of u du. The differential of f of u dwu is f sub T dWt. Okay. So again, if you're not used to this, then this looks like a bunch of voodoo magic to you. But what happens is this, right? When we write this, it's nothing but, remember, it's a change. Okay, it's a change as t goes to t plus dt. All right, it's a change in whatever this is you're looking at as time moves a little bit. Okay, so first of all, this formula, I hope, right, is familiar. Basically, it says that if you add up the small change, you get a big change. Here it says that if time change a little bit, right, if time change a little bit, then of course, right, what's the difference? If you look at the t plus dt, right, and minus from t, right, this is what you mean by d of this. This is what you mean by d of this. But if you look at this, right, you see it's going to be just from t to t plus dt. Okay. But if the time interval is very small, then you can approximately say that the function value hasn't changed that much, or it's going to be the left-hand point times the net change. Like the kind of idea that you approximate the area under the curve, right? This is t plus dt, right? This is the function f. You say the area under the curve, right, which is this, is approximately the value of the left-hand side times the area. So that's the rectangle. That's all you're expressing here in this formula. Okay. Same thing goes for this. Same thing goes for this, except that, right, the change, right, is w to dwu. But again, this is the same idea that when you replace with dwu here, the same thing. Okay. From t to t plus dt, the Brownian motion had changed an amount like this, dwt. All right. So with that notation in mind, the Ito formula can be written like this. df twt is f sub t dt plus f sub x dwt plus 1/2 f sub xx dt. Okay. So what I want to say is, right, this is what I call the differential formulation of the Ito's formula. It's the same exactly as saying do you see that? Right? Because when saying these guys are equal means when I integrate them from s to t, they're all equal. But if I integrate from s to t of this guy, then I get exactly the difference from the first part. The right-hand side are just the integral of these three pieces, and I keep them fixed. And of course, right, the above formula that you saw was just bringing, right, this piece to a left or this piece to a right. All the other pieces are the same, and I group the dt integral together like this. Because they're both dt integral, they can be grouped together into one single piece. And you can look at that as three integrals if you want. Is that okay? So Ito's formula is something you want to memorize and be very quick with in this class because we'll be using it again and again. All right. So I know the first time you see it is strange and it's a bunch of things you have to put your mind together, but just treat it as calculus. Just, you know, you must be able to do it quickly. For example, right? Do it with me. What's dt times wt? What should it be? First, differentiate with respect to t. So you get wt dt. Second, differentiate with respect to w. You got t dwt. Differentiate twice, you get nothing. So that's the answer. How about d of e to wt? Well, first differentiate with respect to t. There's no t, right? Differentiate to wt, you got e to wt dwt. Differentiate one more time. I don't know, cosine of wt. Again, there's no t terms. Differentiate with respect to w gives you minus sine. Differentiate one more time gives you cosine. Right? D of, let's say, t squared e to wt. Differentiate with respect to t. Differentiate with respect to w. Differentiate twice with respect to w. Something like this. Maybe to change it up. Differentiate with respect to t. Differentiate with respect to w. Differentiate twice with respect to w. Any question? And again, right, these are not abstract formulas. What they mean is you can put them together and make sense out of them in terms of integral, right? An integral can be computed using our simulation, our code, right? For example, let's take this guy right here, right? What this guy right here is, in terms of integral, is, it says cosine of wt is 1 minus the integral from 0 to t sine of wu dwu minus 1/2 cosine of wu du. Right. Are we okay with this? So for example, right, write Python code to verify Ito's formula. How would you do this? What's the idea? How would you go about doing some question like this?
Are you asking us to prove it, or just like we're just verifying?
No, right?
Use a bunch of
Sherry, we are
Okay.
very far from proving anything in this class, right? Because, yeah, and that's the difference too. Proving means abstractly prove it's true for anything, right? Your question actually is very interesting. For example, I think everyone knows this. Ax squared plus bx plus c is equal to 0. What is x?
Oh, that's the project formula.
Yeah, which is?
Minus b plus minus square root of b squared minus 4ac over 2a.
Yeah. Now, I think any one of us remember that one time when this formula terrifies us, right?
Yeah.
I remember this when 7th grade, I think, when I saw his formula, I did not know what it means.
It's definitely a formula we've seen like time
Yeah.
and again.
But in terms of Cherry's question, right? If you ask a 7th grader to prove this, can he, she do it? Well, if he's a future math major, you know, math, whatever, right? I think maybe. But a teacher, right? A 7th grade teacher, a reasonable one at that, I think, would not ask them to prove it, but ask them to do what? To
I think maybe just like compute x in terms of like.
check the formula, right? For
Oh, and
example,
see if it
say
works within the equation.
x squared
Right.
plus 2x plus 1 is equal to 0, then x must be minus 1. But then you can check with b equals to 2, a equals to 1, c equals to 1, right?
Okay, so then if after you get your x, then you just plug it in to see if it's correct.
Correct, exactly, right? But basically, the point is, right? Checking the, I'm explaining Cherry's question of from checking the formula to proving it abstractly are two different steps, right? Of course, checking the formula somehow, if you're kind of deep into this, you could see something that allows you to write an abstract proof. But proof is nothing but saying that, right? An umbrella statement that somehow covers every checking case, right? Proof means that any shows that somehow for any ABC this works. Checking means just calculating, right? Calculation. For some particular A, B, and C, it works. These two actually are very, strangely enough, not that far apart. But this is straightforward, and this requires some thought. Yes.
Okay,
So
yeah. Sorry, so will we just like test two formulas, I guess, and then that's sufficient as long as they're equal? Like,
but then how would you devise a plan, right? Because I guess you're not a 7th grader anymore. So I'm not giving you more specific instruction than, you know, doing this. But so what is an adequate plan to do this, right? What would you what would be a plan that would be seem reasonable to check this? So again, right, Ito's formula says something like this. Well, where is it, right? Something like this. Just like the, you know, the quadratic formula example, right? What's the first step for you to do when you want to check something like this? To make it concrete, right? Again, the quadratic formula is hard when A, B, C's are abstract entities. But if you say it's 1 to 1, then it looks much more reasonable, right? So in other words, here, I asked you to verify it, but of course, you just pick some favorite choice of yours for F. Does that make sense? So the first step is just pick some choice of F. Right? But what's the easiest choice possible? Because, right, I mean, verify the Python. I didn't say verify it for any crazy thing, but let's stick with the easy one first, right? What's the choice for f? That's easy. How about f of tx equals to?
Can I just do t or?
T is okay, Don, but again, I think I have a little bit of a not a reservation for picking the term. Or was it Don and Cherry? I forgot. You know, like reservation for picking deterministic integrand, right? Because we're in stochastic context. So how about I choose x?
Oh, okay.
Right? I mean, doesn't matter, right? T is perfectly fine too because Ito's formula is supposed to cover all. And maybe after you do x, you can do t, right? But what do I mean by this? That means that I would do, oh, sorry, x is too easy, x squared, okay? Because you know why x is too easy? Because if of x is x, then what it says? It says, right, dwt is, right, then f of wt is wt. Then the formula says dwt is dwt, isn't it? Because the first derivative is 1, the second derivative is 0 with respect to x. There's no derivative with respect to t. So there's nothing to prove there, right? I mean, that's just that. So I think the first easiest thing to do may be x squared. Is that okay?
Yeah, that makes sense.
So f of wt is wt squared, right? And so Ito's formula says what? Ito's formula says dwt squared is 2wt dwt plus dt. Again, right? Now you also want to make it concrete in terms of the limit, because right, the limits here we write in the abstract as to t. When you're testing it, you know, coding needs the numbers, right? So how about from 0 to 1? In other words, let's say the integral from 0 to 1 of dwt squared is the integral from 0 to 1 of wt dwt plus the integral from 0 to 1 dt. What is this left-hand side? What is this left-hand side? And what is this? I hope you see this is 1, right? And this is w1 squared. Are we okay with this? It's really w1 squared minus w0 squared. But because w0 is 0, we don't need that. Unless you want to do from 1 to 2 or something, then you need w2 squared minus w1 squared. Are we okay with this?
Yeah.
So what this says, right, is so actually I think this is enough. This is enough. So you see, you work out the math a little bit, right, to see what you need to show. So what do you need to show on Python? Well, you need to generate, right? You need to partition zero to 1. You need to generate the ground motion, right? And then what else do? You generate the integral, right? Or the partial sum. Right? And again, right, you understand this partial sum is meant to approximate this guy, right? Now, do you have the value for this one on your code? You do, right? Because when you generate a bar motion, what we mean is you generate an array of values for the values of the bar motion, right, on these grid points. So obviously, because your grid point is from 0 to 1, W1 is the value of the last point on the array. Is that okay? So you have access to W1, right, from your bar motion generation. Right, the whole point of generating bar motion is actually you have access to all values of bar motion at all these points. So W1 is the last point on the array. So therefore, right, you just have to plug in and make sure that it works. Okay. So in fact, right, a more elegant way to do this, and it doesn't have to be done this way, is you can check, right, when you form your partial sum, it will be, I don't know if I did this or something, but like that. It's the same thing, right? So basically you compute this number, and they should be equal every time you run it. Any question here? Notice there is no expectation here, right? So there's no repeating. There is implicitly there's a repeating here actually, but repeating means that you could repeat like 1,000 times, and each time you repeat, they should be approximately the same. Question? So, right, even though I said this is homework, I also did this for you in the other code. So let's see. Right here. So you see, I was computing, right? Actually here, I was computing the integral, right? The Ito integral, right? As I said, this is the integral of WT dWt from 0 to 1, because I picked t equals to 1, right? You see, this is the partition where yeah, I did not really need to partition the time interval because all I need is dw, right? And I need the w. So here, right, I generate the prime motion, right? This is the generate the prime motion, right? So in here, right, this is exactly if you want generate the dw, right? And so the integral of w dw is just adding, right? And okay, so if I want to know what the value is, right, it will be, because I keep adding, right? So here I store the value of the integral as an array, right? So here is like the value of the integral up to that point I, that value time I on this, right? Whatever that I is. So if I want to know the integral from 0 to 1, right, 0 to 1, then obviously I have to call the last value in my array for the Ito integral array. Is that okay? Right, this will be the last value will be the integral from 0 to 1. See, this is the theoretical value that I was talking about, right? W squared minus t over 2, right? And if my Ito formula is correct, they should be similar. And let's see. Ignore the stratopic, ignore these two for now, okay? I'll explain them, but do you see? So right, minus 0.1 minus 0.12, you may say that's not too close, right? Let's run again, but not too far apart. What's the reason why they're not too close? What's the reason why they're not too close here? Or how would I improve the closeness here if I want to convince, right, my audience that it actually is very close or actually is equal? How do I improve this? by making this number of time steps smaller, bigger, right? By making the dt smaller. So let's do this. See? And if I make it even smaller, right? Or make this even bigger, then I'm not sure that it looks like it's improved a lot. But so this is what we mean. And you see, every time I run it, right, it's a different value because it's stochastic. Yes, that's the whole point. The Ito integral is a stochastic process. So every time I run it, it's a different values. But no matter what I run, they're all the same. And by the way, right, this is the path of the Ito integral, right? That's the whole point of storing the Ito integral as a array, right? So that I can have a path of the integral. So you see, its path, this is a Brownian motion path. The path of the Ito integral, in this case, the dw path is very different from the Brownian motion path. So you see, again, my point being is, right, I mean, I know stochastic calculus is a vast subject and can get as theoretical as you want, but the point of this class is I want you to see that you do not have to get stuck with a theory, all right? You can bring this theory to life, right, to in front of your eyes with this calculation, with these numbers. What it takes, though, right, is to be able to willing to be able to think about this in coding, and I think it's a practical skill you want to get. Any question here? Okay. You have an idea what you should do if you have to do this on homework?
Slightly.
Slightly?
Yeah.
Okay, slightly is good enough. If completely lost, then that's rough. But slightly, I think it's okay. We can work with slightly. All right. I think maybe this is a good time to take like I think a 5 minutes break. All right. Let's come back at 5 8 whatever. Let's come back at 10:35. All right, 10:35 my time. So whatever that your time is, let's take an 8-minute break. Okay. I'll see you.
Okay, sounds good.
Okay, so let's start again. Any questions so far about what we've been doing? All right, so next, right, I want to go back to the theme of the choice of the, oops, sorry, did I share? So I want to go back to the theme of the choice of the grid point, right? In terms of the effect on the integral. Okay, so importance of grid point choice. So it's like this. So for example, if you actually, let's go back to this. That what I say was, right, the Ito integral will be the sum of the left point approximately of WTI plus 1 minus WTI. Okay. And so when we choose, right, if different choice of the TI, right, will result in different limit. Okay. So for that, let us go back to like something we're very familiar with. So for example, let us explore the integral like this, WT to dWt, right? So the fact that, so first of all, right, for the Ito's integral, the integral from 0 to t of Ws dWs will be Wt squared minus t over 2, right, as the this formula says. Now, is that surprising? Okay, is that surprising, or what should you expect when you look at an integral like this? So let's explore the what happens if the function is differentiable in time. So what if, right, we use a differentiable function in t? Okay. So for example, let's say that you were using let's say that we have the integral from 0 to t of, let's say, s ds. Okay. What should this answer be? Well, I hope it's clear that it's going to be t squared over 2, right? What about the integral, let's say, of e to the s d of e to the s? What would that be? Well, remember, right, that when you have a differentiable function in time, this will be the integral from 0 to t of e to s, right, e to s ds, because that's the derivative of this with respect to time. So in other words, you got e to 2s ds. But it's pretty easy to verify that this is going to be e to 2t, right, over 2. Is there a minus 1 there? E to 2t, yeah, e to 2t minus 1 over 2. okay? But don't be mistaken by this 1/2, okay? This one right here actually comes from the value of the exponential at time 0. This comes from the value of the exponential at time 0. So maybe let me choose something else that has value 0 to compare with this for you. So let me choose something else. Let me say maybe something like sine, okay? Let me say this, okay? How would you integrate this? Well, first of all, right, d sine s is sine s cosine s ds, right? Now, you may think that, well, this sine cosine, I have to use some double angle formula or something. You could, but the point of thing is that here is a perfect u substitution, right? Because if you let u be sine, then du is cosine. So in other words, this is the integral of u du. In fact, you see, like, that's the whole point of if this function is differentiable, right? Then everything convert back to a integral of u du, which will be, right, u squared over 2 evaluate at 0 to t. And if, you know, the function value u of 0 is equal to 0, like the sine function of this function, then you just get u at t squared over 2. So that's going to be sine of t squared over 2. Okay. So what I'm trying to tell you is that the usual calculus rule, right? If w is differentiable, then the integral, right, of w dw should be just wt squared over 2. Is that okay? It should be just wt squared over 2 instead of wt squared minus t over 2. But, right, that's exactly the point where the simulation helps us, because the simulation allows you to check that, yes, indeed, you need the minus t, right? Without the minus t, it will not be correct. Okay? On the other hand, I said, if you choose different values here, you will get different limit. The demonstration of that is this, that if you were to choose the midpoint choice for the integral, right, of 0 to t ws dws, this is no longer a Ito integral, but it's called a Stratonovich integral. And so to differentiate that, people usually write a circle here. Okay. And the value of this is going to be sum of the midpoint, so it's WTI plus 1 plus WTI over 2, right? Because it's the midpoint. Is that okay? So with this midpoint choice, the value of these conversions will actually converge to WT squared over 2 without a minus t. Without a minus t. So the Stratonovich integral, right? If you do this with a midpoint choice, then it will converge to WT squared over 2. All right. And so that's why it's very important for us to pay attention when you do simulation, which point you choose. Now, obviously, right, I don't think in coding you will mistaken the midpoint with the left point. But trust me, you might mistaken the right point with the left point. Okay, and I will demonstrate that for you. But obviously, right, so first of all, we don't do this in math finance, okay, for some reason I'll explain. But this integral is very popular in engineering and other discipline, where what they want is somehow they want the integral has the effect of something similar to the chain rule in traditional calculus. Okay. So what I want to show you again, right, is a simulation. I could ask you to verify this, but what I want to show you is a simulation, right, where, let me see, right, that here for the Stoyanovich integral, all right, for the Stoyanovich integral, you see what I did was I used the midpoint, okay, and what happens is it should converge to only the final point divided by 2, and that's right here. You see this, notice that this value is very different from this value, and this is the square of the value of the Brownian motion divided by 2. So these two, right, just the choice of the midpoint and the choice of left point will be resulting in different Ito integral. Okay. Now, several things, right, that bears in mind. Now, for example, a very easy error in coding is something like this. Let me see if I can. Suppose, right, I mean, I don't know. Suppose, I think naturally you would do this, but suppose you do Wi plus 1 times Wi, okay? Because you say, right, it's a Brownian motion times dW. Well, how would that, you think, right, this will be an innocent change, but let's take a look at the output. You see, you just change this to a next index, but notice the result is wildly different from the theoretical value. Okay. Now, I think I made a mistake last time that is somehow way more harder to spot than this. I think basically I rearranged my index in a way. I think, actually, you know what? I think I did this. I'll show you, okay? I still keep this, but what happens is I change, instead of range like this, I do this. All right, and let's see that I think it doesn't come out right. Oops. It says index out of bound. Maybe like this. Let me do something like this. Okay. Nope. Okay, anyway, maybe I'll just do this then. So anyway, I mean, so this is the same, right? But if I change this, then it will be different. Now, let's go back to so one thing I could do, right, is basically say this, like a question for you is something like this, like, you know, write Python code to demonstrate that the Ito integral depends on the choice of the grid point but the Riemann integral does not. Okay. So do you understand what this question asks for and how you would go about doing this problem, for example? Right.
Sorry, I'm a little confused because I thought we were only using the left point. So
No, that's true. That's true. So this is more, you're absolutely right, Sherry. Like from now on, right, we will only use the left point. But the question is, if you don't see the difference, right, then you may suspect, I don't know, again, right, that why is it that you asked me to use the left point? Because, you know, several things, right, that like I showed you in the simulation, that you may mistakenly use the right point when you think you're using a left point. That actually, I think from coding point of view, you see, it's easy to happen because instead of, you know, you use one index, you use the other, right? That's one thing. But the second is there is a point to this. That is, you know, like if you don't see that there's a difference, you won't pay attention. So it's really just a homework that shows you that you have to be careful. It's not like something we'll be keeping on using later on. Does that make sense? But
okay.
to demonstrate this idea, how would you do it, for example? That's my question. But yeah, for once we're done with this, we will not repeat this. In other words, I'm not going to keep asking you to play with different point choice, you know, in the future. But for here, right? I mean, at least when we see this, you should at least see something for yourself. So is it okay for everyone to see that this is what you should do with this? So there are two parts to the question, right? There's the Ito integral question, and there's the Riemann integral question. So in other words, right, what I ask you to do is, one, right, you perform the Ito integral with, you know, different choice. Right, maybe like left versus midpoint. And then you observe that they're different. Okay, so I shouldn't even call this Ito integral, right? I should call this the stochastic integral, the dw integral, because, you know, Ito is reserved for the left point. I'm not sure if that's what Sherry was confused.
Yeah, that makes a lot more sense now.
I apologize. You're perfectly right, and I think that's a mathematician in you, right? You see the term, it must have a meaning. I agree. I have in mind like different ways to do a dw integral. Yeah, no. I'm sorry for being inconsistent. This language, you're right, right? So the dw integral, okay? But here, maybe then maybe let me say the dt integral, right? So when you perform, right, perform the dt integral with different grid point. Let's say again, left versus mid versus right, you will get the same value. Okay, and that's what you want to do. So there are like maybe 5 different calculations, but right, hopefully you see then again a difference between these. Okay, so right, just some examples of that. Now, so right, like Sherry very clearly pointed out, right, the dw integral we're using in this class is going to be Ito, because I mean, if people use any other integral, they have to indicate the difference. So, for example, with the Stratanovich, there's a circle, which again, right, we won't use. The Ito is a dot. All right. So now, let's move on with the the lecture, right? So, using Ito's formula in the Black-Scholes model. Okay. So remember, right, my goal is like this, and that's from day one when I introduced the Black-Scholes model to you, I said we want to establish the following, that the Black-Scholes formula has 3 formulations. This is in terms of percentage return, in terms of log return, and in terms of the explicit formula. Okay. So what's the connection, right? Connection between the three, because obviously we want to say that they all say one and the same thing, which is the model for the stock. So how do we do that? Well, first of all, right, let's call this 1, 2, and 3. So 2 implies 3 is straightforward. Why? Because notice this is d of something, right? This is a differential. So if you integrate on both sides, right, you should get the integral like this. Sorry. Okay. Now, what is the left-hand side? This is d of this. So it becomes the change in the log. The integral in dt gives you the integral in dwt gives you, well, technically speaking, right, it should give you this. But again, right, because w0 is 0, right, same as actually technically it should give you t minus 0, right, if you want. But that doesn't matter, right, because t at 0 is 0, so we don't even do that. But right, so anyway, right, you see, if you pull a log on this side and exponentiate both sides, right, and of course this becomes 3. Is that okay? So 2 implies 3 is easy. Now, how do I do 3 implies 1? So you see, 1 is really a formula for dst, right? 1 is a formula for dst. So actually, you see, that's exactly Ito's formula for you. That it says that to go from 3 to 1, you have a formula for st in terms of t and the prime motion. You just have to find dst. Okay. So again, let's repeat that. So st, right, is s0 e to the mu minus 1/2 sigma square t plus sigma wt. So what is dst according to Ito's form? Right. So dst is, first you differentiate with respect to t. But when you differentiate with respect to t, right, you only bring this part down. And everything else is the same. So in other words, we can say this is mu minus 1/2 sigma square st dt. Okay. Then you differentiate with respect to w. Well, what do? You bring the sigma down. So it's sigma st dwt. And then differentiate with w twice. What do? You bring down the sigma twice. So that's going to be 1/2 sigma square st dt. Is that okay? Well, but what is, these two, they have opposite sign. So all in all, you got mu st dt plus sigma st dwt. And that's the percentage return formulation. Okay. Now, so the last one then maybe is the connection, right, from 1 to 2 or 3 to 2, right? Because we show 2 implies 3 and 3 implies 1. So to show that they're all equivalent, we need to connect back to 2 somehow. But the connection back to 2, right, is a little bit different. The reason is this. The reason is, right, the Ito's formula, as what we've been talking about so far, tells us that if we have a function of the Brownian motion, then we can say something like this. Okay. But notice that if we want to go from, let's say, 3 to 2, then st is a function of the Brownian motion and t. But this is not d of st. It's d of log of st, right? So in other words, what's going on is like you have a function of the Brownian motion, right? And let's call this x or s if you want. Then we get another function in terms of t and x. And then we want to do the d of this. Is that okay? So in terms of calculus, it's slightly different. It's the same idea, but it's slightly different from, let's say going from 3 to 1, because 3 to 1 is straightforwardly st is a function of t and w. You want to find dst. But from 3 to 2, for example, is st is a function of t and w, but you want to find d of the log, meaning d of a function of st rather than just dst. So the right formulation is, if I have a function of t and w, what is d of, sorry, not f, right, g, a different function. Okay, what is d of that? Oh, no, I'm right. What am I saying? It's right. You have an original function of t and w. You have a new function, right? You want to find that. Okay, so here g, right? G is like log of xt if you want to talk about. Okay. So let me say this, right? So this is going to be some kind of like the last version of Ito's formula. But for that, let me just introduce something called Ito process. So xt is an Ito process if it's going to be a Riemann integral plus a Ito integral. So in other words, anything that can be written as a Riemann as a dt integral and a Ito integral is a Ito process. Okay, so everything we look at in this class will be an Ito process. So in some sense, we don't need to even highlight it. But there are some processes that actually not Ito process. For example, if you look at, let's say, the max of the Brownian motion. Okay, so this is the max of the Brownian motion on 0t. This is not an Ito process. And it has importance for us because the max like this will show up in exotic option, like look back. Okay, so most of the process we look at in this class will be Ito process, but sometimes we look at some non-Ito process, and how to deal with that is going to be a topic we're going to tackle on later on. Okay, but for now, right, let's just deal with the easy ones. So in some sense, right, it means that it's kind of differentiable. It's differentiable in t. Its change in t can be decomposed into a change in dt, change in time, and a change in Brownian motion. So in some sense, still very nice. Okay. So if it's an Ito process, then if you want to apply, right, Ito's formula on it, like this. Okay. So if you are given a C12 function, then if you want to apply Ito's formula on it, it's going to be f sub t dt Okay, so the change in t is captured with dt. The change in x is captured with the differentiation with respect to x. The change with respect to t needs to be captured with the second piece, but this piece will be called the quadratic variation of x. Okay, where, of course, right, dxt are these. So alpha t dt plus beta t dwt. The quadratic variation of x will be beta t squared dt. Okay. So, all right. Again, looks like a bunch of abstract formulas, right? Do not be afraid. Okay. What's going on here? What's going on here is, right, that basically the philosophy is you want to reduce all action of the processes we consider, if we could, into the action in terms of dt, right, the change in time, and the change in Brownian motion, right? Any other process, like, the in-between, like, Ito process like this, then sure, right, its action is, so basically, it's going to be a middle step, right? This is the chain rule right here. You look at the action of this function in terms of, x, but then the message is that it can be decomposed ultimately back to the action in terms of Brownian motion, in terms of the differential, the change of Brownian motion. Even the second derivative terms is still, right, related to dt, but in a more complicated way, because this one has to be square, right? The term in front of the Brownian motion has to be square. Okay, let me demonstrate. All right, let me demonstrate. For example, okay, example. Suppose that dw, so we looked at before, right? dwt squared is 2wt dt plus, right, 1/2 times 2 dt, which is, sorry, wt dwt, which is 2wt dwt plus dt. All right, like this. Suppose I want to look at a function of wt squared. Let's say dwt to the 4th. Okay, but the catch is this, right? The catch is I do not want to look at this as a 4th function, the 4th power of w. I want to look at this as the square of wt squared. You understand what I'm trying to say? So I want to, in a crazy way, right? Of course, I can just look at this as a 4th power of w, but I want to look at it as a square of wt squared to apply this rule right here. Okay. So again, right, this is viewing things from different angles to show that, the results are the same. So the mathematical results are consistent. So in other words, right, I'm applying the above result with the x process being wt squared. Okay. So if I do that, right, then first of all, you see the alpha is 2wt. This is alpha right here. And the beta, of course, right, is 1. So it doesn't show up, unfortunately. But that's the beta. Okay. So if I apply, right, the dxt squared, right, according to the above formula, okay, dxt squared, then it will be, so the function is squared, right? I will get 2xt, but it's 2xt dxt, and then 1/2 times 2 times dxt like this. Well, now I will convert everything back to Brownian motion. Well, what was xt? Xt is wt squared, right? And then dxt is right here, right? Because that's dxt. So it will be wt 2 dwt plus dt. And then I have this term, which is plus, right? What's the quadratic variation of x? So this is called the quadratic variation process, right? This is called the quadratic variation of x. What is it? Well, it's going to be beta square dt, but beta square is 1. So it's just going to be another dt. Okay. So all in all, what do I have? What I have is, right, plug it together, I have 4wt cubed, right, dwt, and then plus 2wt squared plus 1 dt. This doesn't seem, somehow this doesn't seem right. Give me a moment. Sorry, something is quite wrong here. I'm not so sure where I make a mistake. If I look at xt as 2wt dwt plus dt, then dxt squared is 2xt dxt plus the quadratic variation of xt. Oh, sorry. I am being stupid. I identified the alpha and beta wrong. Sorry. The alpha is a du term. The beta is a dw term. Okay. So here I completely misidentified the alpha and beta. I apologize. So what I said above is completely correct, all right, up to here. I just misidentified the alpha and beta. And that, again, I think I made the mistake too many times today. That the dw and the dt serve very different roles. So we want to pay attention, right? So sorry. So this is my beta, and this is my alpha. Is that okay? No, I still did it. I still commit the wrong error because I just somehow my brain just want the alpha to come first, alpha and beta. Is that okay? So here, right? So the quadratic variation of x is actually going to be 4wt squared dt. Because you take this square. Okay. So then you got, right? Basically, you got 2wt squared dt plus 4, so you get 6. And that's the final answer. So sorry for the messed up, but that actually does happen all the time. So to conclude, right, what did I do? I did a complicated way to find dwt to a fourth via my formula, right? My Ito formula for an Ito process like this, which is like, you can think of it as a general Ito formula, okay? A generalized Ito formula. Because when x, right, when alpha equals to 0 and beta equals to 1, then this is just the other Ito formula, the original Ito formula we talked about. So, okay. So I was applying that formula to here to get dWt to a fourth. What is the point? The point is that this should agree with the original way we do it. That is, when we do dWt to a fourth, right? We say, well, just differentiate this with respect to W, you get 4WTQ dWt. Then differentiate one more time, you got 1/2, right, times 12 WT squared dt, but that's exactly 6 WT squared dt. Is that okay? So this example I was doing was just demonstrating to you that this formula is indeed consistent. This formula is indeed consistent. What you need to remember though is, right, the quadratic variation term here is the Brownian motion term square dt. Any question? All right. So again, I do realize, right, that's a lot of formulas for you to, keep in mind in one day. I will kind of recap this, all right, in a more consistent way at the end of the class. But so the goal right now, right, is for us to show that 3 implies 2, okay? To show that 3 implies 2. So we will use the new formula, the generalized formula, to show that 3 implies 2. Okay, so again, 3 is St is S0 e to the mu minus 1/2 sigma squared t plus sigma Wt. And then 2 is d log St is, what is it? Mu dt plus sigma dWt. So actually, okay, to be technically correct, I have 3 implies 1 implies 2, but that's the same, right? Because that means 3 implies 2. Why is it that I need 3 implies 1 implies 2? Because I need to have dst, right? I need to have dst to continue with this calculation, all right? Because like the Ito formula, right, requires you to have dxt. So x here is s, right? So I need dst. So 3 implies 1 gives me dst is mu st dt plus sigma st dwt, as we showed. Okay, so how does 1 imply 2? 1 implies 2 when you do d log st. Well, so the function, right, is log. So first you differentiate with respect to the log, you got 1 over, right, x times dx. And then you do differentiate one more time, which gives you 1 over s squared, right, minus. And then the quadratic variation, what is the quadratic variation? Right here, right, the dw term. You square this, so you get sigma st square dt. Is that okay? Any question here? Well, so now you plug in, right? So this is just formula, but now you plug in, right? Actually, you use this from this part, and then you plug this in here. Then you get mu st dt plus sigma st dwt, right? This and this cancel, giving you minus 1/2 sigma squared dt. Well, but then also this and this cancel, right? Giving you all in all, mu minus 1/2 sigma squared dt plus sigma dwt. Any question? So remember, right? Remember, actually, I said this has very deep financial meaning, that the log returns, right? Remember, the log return is lower than the percentage return on average, right? It's this versus this. And you confirm that, right, with the simulation. So exactly, you see, and you can also confirm it with real data, that basically the log return is smaller than the percentage return. But then mathematically, you see, where does this -1/2 comes from? The -1/2, right, comes from the second derivative term, which again comes from the Ito's formula, which again comes from our choice of construction for the Ito integral. Okay, so what that means is, right, when it comes to modeling, I hope you see that modeling is a complicated process, right? When you say, okay, W is my source of noise, fine, right? People won't argue with that. But how do you put together your source of noise to construct your stock price? And you see that, right? With that question is, how do you construct your integral? How do you add them up? Okay, and I hope I demonstrate to you that there's more than one way to add. You add it on the left point, you add on a midpoint, you add on a right point, okay? And at least, right, you see that adding on the left point makes sense at the stock price level because it produces some phenomenon that we can observe that is consistent with reality. That is, the log return is lower than percentage return. If you were to use the Stratonovich integral, right, the midpoint, then the second derivative will not show up. The second derivative will not show up. Then I guess the implication of that is the log return has the same rate as the percentage return, which probably will not be what you observe in reality. Okay, so the math that we do, right, even though very abstract, has a connection with, right, what we try to model. And of course, right, again, I'm not trying to say that we are like, we're so powerful, we can see the reality, so we just make our math works like reality. No, it's more like there are different choices, okay, of how to construct our model. And the choice that we choose happens to be corresponding to reality. So in fact, then we go with that choice, the Ito integral, right? Because that somehow matches what we want to do in finance. The engineering has their own world to model, right? And in their world, the Stratonovich integral matches the phenomenon better for them than the Ito integral, right? They probably don't see the second derivative hanging around. So for them, they definitely don't want to do that. And so a better tool for them to model is not the Ito integral. But for us, right, for finance, the Ito integral is the tool, right? Is the right tool to model. And of course, what comes with that is, the second derivative terms that we need to always take care of. Okay, any question? So this is basically the heavy duty math that we need to talk about. Okay, when we in the Black-Scholes model. After this, we're gonna explore the financial aspects, but like the mathematical foundation should always be kept in mind because all the things we do will be built upon this. Okay, so to recap. Okay, to recap, what do we have, right, in terms of Ito's formula? So to be frank, right, Ito's formula is actually very easy in this way. That and actually is also a explanation of why it works. Why it works is actually something called Taylor series expansion. Okay. So if you have a function in T and X, this is like your calculus 3. And suppose that you change T with delta T, and you change X with delta X. Then what does Taylor series expansion tell you? this is approximately the original point plus the derivative with respect to t at the original point times the change in t. And then, you know, of course, you can do this. The first derivative change in x with respect to x, right? This is called the linear approximation. Right, of the function using the first derivative. So what you're saying is like you draw a line, right? Or you draw a plane, whatever, right? And you say that the direction changed a little bit. So if I follow that tangent plane, right? I follow the tangent plane, then I can go from t to the new point, and I can be approximately close to the curve, right? Tx. Okay. Now, of course, the linear approximation is not the best approximation or the only approximation you can do, right? The whole point of Taylor expansion is you can just keep expanding this to get more and more precision. So for example, you can do the quadratic approximation. So first you keep this, right? And then you do this. And then you do the second derivative terms. Right. This is called a quadratic approximation. So what's the point? The point is, right, the quadratic approximation will be always better, right, in terms of the linear approximation in terms of error. Of course, the cost is that if you cannot differentiate twice, then you cannot do quadratic approximation. But if your function is nice enough that allows a second derivative, then second order derivatives, then you can, you know, the approximation will become better, right? And you can push it to the third derivative, etc. And actually, right, maybe I missed this. There's also mixed term. Actually, there's going to be 2, right, times 1/2, right, of f of tx like this. There's going to be a mixed term too, delta t, delta x. Okay, like this. So anyway, right? So in our context of Ito's formula, okay? So you have, let's say you have a process xt, okay? As a process in t. All right. Then as t goes to t plus dt, all right, or t plus delta t like this. Then xt goes to xt plus dt. Okay. So the delta x that we look at, right, the delta x here, or usually we call dxt, right, will be, right, this guy minus this guy. But isn't that, right, captured by exactly what we say, you know, the model? In other words, we say, well, it's going to be captured by some change in dt and some change in ground motion. So in other words, the delta x in turn is captured by some function in t and some function in terms of the ground motion. Okay. So anyway, let's revisit this later. But let's just say there's a delta x. Then if you do the if you do the Taylor series expansion, right? And by the way, right, when you put this over here, that's exactly what you mean by df, right? As time moves, this is df, right? This is a change in f. So what you're saying, right, is again df of txt is the change with respect to time, dt, the change with respect to x, how much x has changed. That's exactly the first order approximation. Okay. Then, well, then you ask, well, isn't that the end of the story? Well, not really, okay, because of some peculiarity. Let's just change the second order approximation like this. And so you realize, right, this term right here is what we denote as the quadratic variation. All right, but in terms of Taylor series expansion, it's just the delta x squared. And of course, there's a mixed term right here too, which we'll explain. But yeah, so why not, right? Why not? There's a mixed term right here. Like that, dt dxt, right? What happens? As you may suspect, the dt squared term actually is 0. It disappears. This term is also 0. Anything higher than the quadratic terms, like if you have like the cube term, right? If you have dxt cube, whatever, they're all zeros. So the key observation is that dt squared is equal to 0. dwt squared is dt. And again, here we meet again that concept where, right, the change in the Brown motion, remember I wrote this at the beginning of the class, dwt is square root of dt roughly. So that's exactly this right here. But this right now you can use as a formal principle. You can use this to compute this. Okay. Now, what do we mean by dt squared is equal to 0? What I mean by this is, so 1, okay? What I mean by 1 is this. Suppose I have a function in t, okay? Let's say e to a t. I have a partition from 0 to 1. Then I can compute, right, the integral of et dt squared. Just the same as your, activity last week. Well, what is this? It's going to be the sum, right, of e to ti plus 1 minus ti squared. And I should take the limit, right, as delta t goes to 0 of this. Now, if I take the limit as delta t goes to 0 of this, what should I get? What do you think I'll get? If I form this partial sum and I push delta t goes to 0, what should I get? What do you think I will get?
Will it getting 0?
Exactly, I'll get 0. And again, right, this is a perfect question to ask you to explore on your homework or on your weekly activity. So you see, right, that's the peculiar thing about integration. I mean, in lower calculus, right, you were not asked to explore this, because all you were asked to pay attention to is the it's hard enough, right, for you to deal with the Riemann integral. But actually here, I hope this is also demonstrating to you why you don't need to bother looking at anything else. Why? Because basically anything less than 1/2 or less than 1 here will be 0, will be infinity. Anything bigger than 1 will be 0. So the just right, is the dt, nothing else. So in other words, right, if you adjust this, sorry, infinity, 0 to 1. Any tiny bit, you will get 0 or infinity, depends on the direction, right? Again, what's the reason? What's the intuition? The intuition is, right, dt is going to 0 very quickly, right? All these dt is going to 0. So if you square a small number, it just gets smaller, right? So 0.1 square is 0.01, right? It's much less than 0.1. But by the same idea, 0.01 square root is 0.1, which is much bigger, right? Much bigger than 0.01. Okay, so when you do square root of dt, you introduce a bunch of terms that's much bigger than dt, so it goes infinity. When you square dt, you introduce a bunch of terms that's much smaller than dt, so it goes to 0. So that's why, for example, let's not forget what we're doing. When we look at the, Ito formula, right? It's not magic that says that you don't have this term. But the reason is because dt squared is 0, so when you integrate, you don't see anything, so you do not write it. What about this term, right? So xt, right? We say x has two components. The first component is the dt component. The second component is the dwt component. Okay, so dxt squared, right, the quadratic variation, will be alpha t squared dt squared, beta t squared dwt squared, plus, the cross term, alpha t beta t dwt dt. Okay, so keeping this key, right, that dt squared is equal to 0, this term doesn't show. dwt squared is dt, so these terms go back to dt. Now, what about this term, right? This term, remember, in principle, dwt is like square root of dt, right? And this is dt. So all in all, this is like dt to the 3/2. But remember what I said, right? Any dt with anything higher than 1 will be 0. So actually, this is also 0. So all in all, all you see is that you only have the quadratic terms, and it's dt. So dt dwt is also equal to 0. And that explains it. Okay, and that explains it. So in other words, right, that the Ito's formula, right, where you have df, right, is f of t dt, f of x dx, plus 1/2 f of x dx squared, right? You can think of it as dx squared. And dx squared is nothing but beta squared dw squared, which is beta squared dt, right? It's because any terms of any other combination will go to 0. And that's it. That's really it. And if you remember, right, the Taylor series expansion, which I think is not hard, then any Ito's formula is captured by that formula, by that principle, and that's it. Any question? So for example, right, let me say this. Again, this is a bunch of abstract principle, but you can check it. So for example, right, I mean, homework, right? Write code to verify dt squared is equal to 0. dwt squared is dt, dt dwt is 0, right? These are the 3 key principles that we assert in the lecture. How, and of course you should trust me on this, but how would you write code to verify this? Okay, this is the last part of the discussion.
Will we take like an example of dt and then dwt and then try to like compute its square and see if it's equal to like 0 or dt or 0?
Okay, so but then what do you mean
Like
by
direct computation.
yeah, but how would you do the computation, right? So there should be some, I think you get the right idea, but there should be something more concrete, right, than what you just say. So for example, right, you should generate, right, dw, yes, you should generate dt, right? And you should generate, so you just choose f, choose a function f. Let's just say ws. Then you should form partial sums. Sum of ws, wti, sum right? Do you see what these sums are trying to do? This is trying to prove dt squared is 0. This is trying to prove dt wt 0. This is trying to prove this is dt, right? And in fact, maybe, right, let's even make it a little bit more easy. Maybe let's choose this to be s. Why? Because this answer is supposed to be 0. This answer is supposed to be 0. This answer is supposed to be, let's say the interval is 0 to 1, right? Then this answer is supposed to be 1/2, because it should be the integral from t dt. Does that make sense?
Yeah, it does.
So, and also, right, you can change with different choice of s, and you see that this is the same. So you can choose this to be s squared, right? This doesn't change, this doesn't change, this changes to a different number, but the number is still consistent, right? And after you do the code, I hope you will see that this principle is exactly kind of trustworthy. Okay. So I think that's the end of the lecture. I will answer any questions if you have about homework, whatever. If not, then I'll see you next week, okay? Or during office hours.
What is the first and second moments?
I think first and second moment should be like the expectation and the variance of an integral, right?
Are you asking about homework question, Sharon?
Yes, the problem 2. What is the first and the second moments?
So first moment, right, means just expectation. Second moment.
Oh.
It should be a variance, right?
Yeah, I mean, it's the same thing. But I mean, technically speaking, right, it depends. Second moment means this, and is equal to the variance if, right, expectation of x is equal to 0.
Okay.
Which is true here, right, for the Ito integral. But if it's not, then the second moment is different from the variance. But here, yes, they're the same question in some way. And I asked, right, basically, I asked you to apply, again, that formula, that principle. That again, right, you can check using code, right? Like that, right? Any other questions here?
I have a question about like 4b.
4b.
Yeah, 4b.
Okay, I
So
forgot.
it says
4b.
like
What is it?
an expectation of an integral of t0 e exponential w with dw in terms of f sw. Is that the same as finding the first and second moment from part 2, or is it something else completely different?
Let me see. Homework 2. Oh, it's different because now it's going to be conditional. Oh, you mean which one? Part B or part C?
Part B.
Part B was asking you about the, okay. So there was another idea, right? That I did not say that, but I said the Ito integral, I said last time, I did not really harp on it. The Ito integral is a martingale.
Right, yeah, I remember that.
So basically, right, when you take conditional expectation of, let's say, a future value,
Mhm.
based on the current value,
Mhm.
all you get is the current value. That's it.
Yes, I remember that.
I'm sorry?
Yes, I remember that.
Yeah. So that's it. That's B. That is not
No need to like get the integral itself, that's it?
that's it. But I hope you
Oh,
see that
okay.
it's a very different principle from the expectation.
Oh, okay.
Right?
I guess I overthought it.
Because the answer without this is going to be 0,
Okay, yeah, I see.
right? But with this, it's going to be based on the value at that time, right?
Okay, all right.
Mhm.
Okay. And I'm also kind of like a little bit confused about 3. Like,
But
I understand how to solve the problem with just like um interpreting the integral in terms of like its distribution.
yeah,
So where it's just like the function has a standard deviation of like the integral of the square of that function. But I remember during office hours when we did like part A, I initially thought that like f squared would be just s squared, but you did s squared over 2, so I was confused about that.
so did I do something wrong in the homework? But it's going to be something like this. So that should be t cubed over 3.
Oh, right. Okay. Okay, then.
Was that what I did, or did I do something different?
Yeah, I remember like last time you did like s squared over 2, so that
Oh,
kind of like threw me off a bit.
no. If I did that, that's probably just a slip of my mind. It should be just
Okay.
yeah.
All right. Just wanted to make sure.
Mhm.
Okay, that's it. Thank you.
Sure.
Oh, and then I had a question. Just so for 4B, I actually got what you wrote down first, and then I went to the officer yesterday, and he said that like I don't know if I asked it in a in a wrong way, but I asked if like if that formula held, because I remember you like using this formula in class,
Mhm.
but he said that we can't use it because it's not deterministic, I think. Is that the case for this formula? Because
Oh,
I have a trouble distinguishing between the formulas that are like when they're deterministic and not.
wait. Are we talking about 3B or 4B?
4B. Just this question like right before like the second last line that you just wrote. I got this at first, but then I changed it to something else with the help of the TA yesterday.
No, because so basically, so this right is not asking for anything involving probability, right?
Okay,
Wait,
the way he did it was using Ito's lemma, actually.
but did he get this answer too? Don't tell me he got something different.
I didn't finish solving it. So he probably it would have been the same, but I just didn't like he gave me a hint and like some resources. At first, because my initial question to him was that if this integral, at first I got this number, like the integral on the right side, but then I didn't like I asked him if I'm supposed to solve it more or if that integral is just sufficient. And then he introduced the concept of Ito's lemma
I
to
don't think we covered Ito's lemma yet. So
No, and then also, right, I don't, again, maybe the TA knows something that I don't, that basically, again, right, what I want you to see here, right, in question 2, 3, and 4 of this homework is there are 3 very different kind of questions you can ask. I mean, related, but different in spirit, okay? In
Right.
2 is asking for the moment, in other words, expectation and variance. 3 is asking for distribution, in other words, probability, right?
Yeah.
You understand 3 is asking more detailed question than 2, because if you know 3, you know 2 in a way, right? But that's why 3 requires the integrand to be deterministic. Otherwise, right, those probabilities cannot be computed. Or you don't know the distribution. 4,
I realized that. Yeah.
yeah, 4, I mean, except for A, right? A is just a covariance question. So A is not kind of, A should belong somewhere else. But B, C, D is about conditional expectation. In other words, right? Yes, it has a flavor of expectation in it, but it's more of, is about taking expectation of the future based on the current information. Okay, so the flavor 4 is not the same as 2 or 3, but right, the flavor 4 can be boiled down to something like this. For example, for B, right, it's all about kind of the past and the present in some way too. So if you do this, right, remember I said the spirit, right, of dealing with this is to decompose the future into the present and the future change.
Yeah.
Okay, like this, right? Now, again, I hope Professor Larson, right, emphasized that the whole point of conditioning is that up to time s, everything like this is deterministic, meaning it's known. So it can come out without any expectation.
Yeah.
Right, because it's known, right? We are conditioning on it.
Yeah.
What about this future piece?
It's independent, so we just like take off the part we conditioned it on.
Yeah, except that, Cherry, you got to be careful here because it's not exactly independent. All right, but you're almost right. The reason why it's not independent is because, yes, the dw will be independent,
Yeah.
but there is the w. All right, that's tricky. The wu is not independent of ws. You understand what I'm trying to say? Wu is not independent of ws because we say the future increment is independent of the past, but the future value is not. Does that make sense?
Okay, I'm trying to process it, but I think I see that.
But nevertheless, you're still right in the sense that yes, this is still 0. All right, you're still right. But the reason is this, that if you want to insist on independence, you better introduce an increment in it. But you see,
I see.
introducing this actually doesn't cost anything because as far as independence goes, this is a constant. So all you have to do is to introduce something like this. Do you understand?
Yeah.
And then, yes, then what you say is right. That means you can drop this. But once you drop this, then expectation of any Ito integral is 0. So it doesn't matter what you multiply in front is 0. So that's the argument. But so in short, this is 0. And that's why this is the answer.
Okay.
Right? But I don't think it involves any Ito formula. It's just really understanding, right? Past, future, and independence of increment. And that's really it. But I mean, like, I was expecting really something even less. That, like you said, if you remember what I said about martingale, go ahead and use it. You know, it's a right application. Yeah.
Yeah, I think I just got stuck because I saw the integral and then I thought I was supposed to do more afterwards, like actually compute a
No,
the variables.
the message there was just that do remember, right, that the Brownian motion, the Ito integral is a martingale with respect to its own filtration.
Okay, I see. Thank you.
Yeah. Any other question?
If no one else is asked, I had a generic question about like the lecture from
Yep.
last week.
Yeah.
I just remember when we introduced conditional expectation and then we said something best mean square approximation to FWT based off the path
Mhm.
of the Brownian motion.
Mhm.
I didn't really like I looked over that formula. I don't know if I should read it out loud or type it in the chat.
That's fine.
It was
What-
like the mean squared error.
Yeah.
And then like one of them has like a risk neutral like sign on it on the top. I just
Oh, maybe because I was doing expectation like this. If I do expectation like this, then it's best mean square error with respect to risk neutral. But you know, like the best mean square error is because of the conditioning. So in other words, let's say this, right? Let's say W U, okay, for T less than U or some, so hold on, sorry. If T is less than U, right? If something like this, right, it will be a best mean square error of, so if I do this and I square it and I take expectation, but because it's all carry on under risk neutral, I must do risk neutral here. So this is best. In other words, if you use any other function that depends on the path up to time t, it will not be as good as this square expectation. But I mean, you can do this under the physical probability as well.
Okay, so by the greater than or equal to sign, you meant best, not the actual value of the expectation.
So by greater than or equal to, I mean, right, let's say you introduce another guess. Let's say, you know, you naively guess the integral. Let's say this. Sorry, let's do S. So you understand, right, that when I do this, this is a guess for this. Right, this is another choice. This is another, sorry, this is another guess for this based on do you understand what I'm trying to say?
Sorry, based on y. Oh, F of the filtration. Okay, yeah.
Based on the path up from
Yeah.
to, right? Again, a wild guess, right? Something else can be also. But basically, if you take the right conditional expectation and you take some random guess and you form the expectation square of both, the top always is less than or equal to the bottom.
Oh, okay. The top is.
So again, let me make an easier statement for you, right? So we know this, right? Expectation of WT condition on FWS is WS, right?
Yeah.
What that means is, suppose you pick some other guess. Let's say you do, so the mean square error is this, right? This is mean square error, right?
Yeah.
This will be always among all the crazy thing you can think of. So what that means is, for example, let's say, you know, I don't know, Dawn like exponential stuff. So let's say she does this. Then this expectation will be less than that expectation.
Okay, I see.
You know, and then you can do cosine whatever you want. This is the smallest.
Okay.
So yeah, maybe I should assign this as a Python homework to demonstrate that. That would be yeah, that would be actually something interesting to do.
Yeah, okay. Yeah, I see it now. Thank you.
Sure, sure. Yeah. Any other question?
If if no one else is asking, also, you know how like Xiaoran and Lena and I are registered for the IAQF?
Mhm.
I was wondering, so our like team plan is that by next Monday we will have like done our estimation is that like we would have analyzed the data sets. Xiaoran and Lena are doing that, and I'm just gonna look more into the papers. But I was wondering if we could have like a meeting with you sometime next week.
Yeah, yeah. Even we can meet this week if you want. I mean, you know.
Oh, I don't think we have any progress yet.
Okay,
for
sure.
this week,
So
but
yeah,
yeah.
I mean, but in case you have anything to clarify, any questions, you know, you want to discuss in terms of direction, that kind of stuff, like feel free to, you know, like let me know anytime, you know.
Okay. Would it be possible for us to like schedule a day with you if
Yeah.
yeah. Okay.
So
Uh maybe like around 9. Is 9 p.m.
yeah,
EST too late?
no, it's fine.
It's fine. Oh, okay. Yeah, I think like maybe next like either Wednesday or Thursday. I don't know if Sharan has any preference. Sharan, are you there? Um, like either Wednesday or Thursday, I guess would work.
Okay, yeah. Again,
Okay.
among you guys, and let me know. Night time is good for me. Yeah.
Oh, okay. Yeah, then I guess Wednesday 9 or maybe yeah, Wednesday 9 p.m. then EST. Yeah, that sounds good. I'll let Lena know as well then.
Yeah, yeah. Let me know. Then I'll be able to meet. Yeah.
Yeah, okay. Thank you so much.
Sure.
Thank you. Bye.
Bye. Sharon, do you have a question?
The part B of the problem 1 in the homework.
Part B.
Yes.
Find the price.
Yes.
So, hold on.